Hello learners, today we shall learn about Chapter 9 Coordination Compounds. Dear learners, after today's discussion, you will be able to understand the term coordination compounds, appreciate the importance and application of coordination compounds in our day-to-day life, appreciate the postulates of Werner theory of coordination compounds, know the meaning of the terms coordination entity, central atom, ion, ligand, coordination number, coordination sphere, coordination polyhedron and oxidation number. You will also be able to identify homoleptic and heteroleptic complexes. Let us start by defining a coordination compound. A coordination compound is one in which the central metal ion in the complex ion forms dative coordinate covalent bonds with the species surrounding it. It is said that coordination compounds are the backbone of modern inorganic, bioinorganic and chemical industry. Is that so? Where and how do we use them? Well, you will appreciate their presence in our life systems, say chlorophyll, hemoglobin and vitamin B12 are coordination compounds of magnesium, iron and cobalt respectively. Variety of metallurgical processes, industrial catalysts and analytical reagents involve the use of coordination compounds. Coordination compounds also find many applications in electroplating, textile dyeing and medicinal chemistry. In qualitative analysis or the salt analysis, we use certain reagents which are coordination entities or certain tests which involve formation of such complexes. Example, potassium ferrocyanide used in detection of Fe3+, Zn2+ is a coordinate complex and the colored species so formed is a coordination complex as well. Another example is the nickel DMG complex, the rosy red color complex. It is interesting to know that we can determine hardness of water by simple titration with disodium EDTA. The calcium and magnesium ions form stable complexes with EDTA. The use of chelate therapy in medicinal chemistry is well known. For example, EDTA is used in treatment of lead poisoning. We are well versed with the fact that tumors are a great health problem these days. Some coordination compounds of platinum effectively inhibit the growth of tumors. Examples are cisplatin and related compounds. Now that we know how coordination compounds are an essential part of our lives, let us understand the chemical perspective of such compounds. Alfred Werner, a Swiss chemist, was the first to formulate his ideas about the structures of coordination compounds. He prepared and characterized a large number of coordination compounds and studied their physical and chemical behavior by simple experimental techniques. Werner in 1898 propounded his theory of coordination compounds. The main postulates are: in coordination compounds, metals show two types of linkages, primary and secondary. The primary valencies are normally ionizable and are satisfied by negative ions. Thirdly, the secondary valencies are non-ionizable. These are satisfied by neutral molecules or negative ions. The secondary valency is equal to the coordination number and is fixed for a metal. The ions groups bound by secondary linkages to the metal have characteristic spatial arrangements corresponding to different coordination numbers. He further postulated that octahedral, tetrahedral and square planar geometrical shapes are more common in coordination compounds of transition metals. Whenever we come across a lengthy complex formula, most of us find it difficult to know whether it is a double salt or a coordination compound? Well, let us find out. What is the difference between a double salt and a complex? Both double salts as well as complexes are formed by the combination of two or more stable compounds in a stoichiometric ratio. However, they differ in the fact that double salts such as carnallite, Mohr salt, potash alum, etc. dissociate into simple ions completely when dissolved in water, while complex ions such as potassium ferrocyanide do not dissociate into ions completely, that is, the coordination entity is retained, only counter ions are formed. Ammonium ferrous sulfate, a double salt, dissociates completely to form ferrous ions, ammonium ions and sulfate ions as well, while a complex like potassium ferrocyanide dissociates into ferrocyanide ion and potassium ions. It does not dissociate into ferrous ions and cyanide ions further. Can you suggest in terms of Werner theory why this is so? Yes, secondary valency are non-ionizable. Let us now learn and understand definitions of some important terms pertaining to coordination compounds. The first term we come across is a coordination entity. A coordination entity constitutes a central metal atom or ion bonded to a fixed number of ions or molecules enclosed in square brackets. For example, COCl3 NH3 3 is a coordination entity in which the cobalt ion is surrounded by 3 ammonia molecules and 3 chloride ions. In a coordination entity, the atom or ion to which a fixed number of ions or groups are bound in a definite geometrical arrangement around it, it is called the metal atom or ion, also referred to as Lewis acids. Can you identify the central atom or ion in the coordination entities shown here? Yes, they are Ni2 plus, cobalt ion and Fe3 plus respectively. The ions or molecules bound to the central atom or ion in the coordination entity are called ligands. They may be simple ions such as chloride ion, small molecules such as water and ammonia, larger molecules such as ethylene diamine or even macromolecules such as proteins. When a ligand is bound to a metal ion through a single donor atom, as with chloride ion, water molecule or ammonia, the ligand is said to be unidentate. While when a ligand can bind through 2 donor atoms, as in case of ethylene diamine or oxalate, the ligand is said to be didentate. When several donor atoms are present in a single ligand, then the ligand is called a polydentate ligand. EDTA, ethylene diamine tetraacetate ion, is an important hexadentate ligand. It can bind through 2 nitrogen and 4 oxygen atoms to a central metal ion. When a di or polydentate ligand uses its 2 or more donor atoms to bind a single metal ion, it is said to be a chelate ligand. The number of such ligating groups is called the denticity of the ligand. Such complexes, called chelate complexes, tend to be more stable than similar complexes containing unidentate ligands. Ligands can also be classified as neutral, anionic or cationic on the basis of charge they carry. Ligands which can ligate through 2 different atoms is called ambidentate ligand. Examples of such ligands are nitrite and thiocyanate ions. Nitrite ion can coordinate either through nitrogen or through oxygen to a central metal atom or ion. Similarly, thiocyanate ion can coordinate through the sulfur or the nitrogen atom. Next we move to the coordination number. The coordination number of a metal ion in a complex can be defined as the number of ligand donor atoms to which the metal is directly bonded. Let's work out the coordination number for the given complex here. Yes, it is 4. Why? Since nickel ion is bonded to 4 ammonia molecules. How about this complex? Did you say 3? No, it is not 3 here. Remember, oxalate is a didentate ligand and that is 2 bonding atoms per ligand, making the coordination number 6. It is important to note here that coordination number of central atom ion is determined only by the number of sigma bonds formed by the ligand with the central atom or ion. The pi bonds, if formed between the ligand and the central atom, are not counted for the purpose. The central atom ion and the ligands attached to are enclosed in square brackets and is collectively termed as coordination sphere. The ionizable groups are written outside the bracket and are called counter ions. For example, in the complex potassium ferrocyanide, the coordination sphere is the ferrocyanide ion and the counter ion is potassium ion. Well, the spatial arrangement of the ligand atoms which are directly attached to the central atom defines a coordination polyhedron about the central atom. For example, cobalt NH3 6 is an octahedral complex, while nickel tetracarbonyl is a tetrahedral complex. The oxidation number of a central atom in a complex is defined as the charge it would carry if all the ligands are removed along with the electron pairs that are shared with the central atom. The oxidation number is represented by Roman numeral in parentheses following the name of the coordination entity. Complexes in which a metal is bound to more than one kind of donor groups, example tetraamine dichlorido cobalt 3, are known as heteroleptic complexes. Well, let us quickly summarize today's discussion. Coordination compounds find extensive use in our lives and various industries. Coordination compounds involve the formation of a dative or a coordinate bond between the metal atom or ion and the ligand. For the given complex, let us work out the following. The central atom. Can you tell what is the central atom here? Yes, the chromium atom or ion. Ligands and their types. What is the ligand here? Well, ammonia and water, both here are the ligands and they are neutral. Yes, as well as they are unidentate. Can you calculate the oxidation number of central atom or ion here? Yes, it is +3. Now, let us find out whether it is a homoleptic complex or a heteroleptic complex. Yes, correct. It is a heteroleptic complex. What could be the primary valency here? It is 3. How about the secondary valency? Yes, it is 6. Let us also find out the coordination number. You remember, coordination number is equal to the secondary valency. Henceforth, it is 6 here. There is a lot more to learn about coordination compounds, which we shall take up in our next module. Before we end today's discussion, let me leave you with an assignment. Explain the term chelate effect and what are its implications on stability of complexes. Also, find out the oxidation number of cobalt in tetracarbonyl cobalt complex. I hope you have understood the concept discussed. Bye for now. Take care.